Hello fellow data enthusiasts and welcome back to UNIP Education. I'm your guide Raffaele, taking you on another journey through the exciting world of statistical analysis. In our previous episodes, I introduced you to the powerful technique of multiple and simple linear regression and how they are widely used in the field of psychological research. We discussed how they allow us to predict outcomes based on a single or multiple inputs. But before we take the plunge and start running our regression models, we must first understand the bedrock on which these techniques stand, their underlying assumptions. So today, we're going to dissect these assumptions, why they're critical, and what happens when they are violated. We cannot conduct a robust multiple regression analysis unless certain assumptions are met. What are the assumptions here? So let's check. We have autocorrelation, we will need this, collinearity, normality, residual plots, and Cook's distance. As you can see, these are all our assumptions. They are quite a lot in comparison to the previous test, but let's go one by one. So first of all here, we have Cook's distance. Cook's distance is basically displaying whether in our dataset there are a certain amount, or if any, outliers. In order to meet these assumptions, we should check the maximum number on the range, and this should be less than 1. In our case, it's good, it's 0.0573, and hence our assumption of outliers is not violated. Outliers can have a big impact on regression models by influencing our results. This is why we have these assumptions over here. After checking for outliers, we have to check whether the residuals in our model are normally distributed. And as you might know already, whenever it comes to normal distribution, our two friends always come to the rescue. It is exactly the Shapiro-Wilk test, which functions exactly as every other Shapiro-Wilk test. So in order for us to meet the assumptions, we should check whether the p is above 0.05. In this case, it is above 0.05, and hence we have respected these assumptions. After normality, we have one of the most important assumptions for multiple regression, which is the Darwin-Watson test for autocorrelation. What does this test do? It's testing the independence of errors. What does it mean? It means that the residuals or errors from our model should be independent of each other. So, in other words, the error associated with one observation shouldn't predict the error associated with another. Violation of this assumption usually stunts you from proceeding with further analysis, in as much as you will inflate type 1 error to the sky. So how do we interpret the Darwin-Watson test? Very simple. P should be above 0.05, as for the Shapiro-Wilk test of normality, so in this case it is fine. And the DW statistics should be around 2, meaning that values between 1.5 and 2.5 are okay. If they are like above or below, not the best. In our case, we have 2.08, and hence that is completely fine. Then we have the assumption of multicollinearity, which refers to high intercorrelations among independent variables. So when variables are highly correlated, it becomes difficult to tease apart their individual influences on the dependent variable. So, for instance, if you have hours spent studying and hours spent on video games, predicting GPA, they will probably be very related, as much as if you are studying, well, you're not playing. If you're playing, you're not studying. So, what do we do in this case? We probably pick only one of them as our predictor variables, or as our independent variables. So how do we check it? We check the VIF, which stands for variance inflation factor, and this VIF value should be less than 10. So in this case we have all scores way below 10, and that is completely fine. Otherwise, you can also check tolerance. And tolerance value should be above 0.1. In our case, they're all well above 0.1, like 0.1. so it is fine. Finally, we are checking the assumption of linearity and homoscedasticity of residuals. So in order to do this, we must check the fitted residual plot. Geomovi, unfortunately, as other statistical software, does not allow us to draw a fit or regression line, but you can see by the way these points spread across this plot that they sort of approximate a line, meaning in our case we have linearity and homoscedasticity of the residuals. What is homoscedasticity? You might remember this from the Levene's test of homogeneity of variances in t-test. It means that the variability in the residuals, in our case in multiple regression is about the residuals, is constant across all levels of the independent variable. If the variance of the residuals changes across levels of your predictors, it's called heteroscedasticity. Homo, same, hetero, different, from Greek, which can lead to inefficient estimates and incorrect conclusions about the significance of predictors. So, in this dataset, all our assumptions were met, and so we can proceed with actual regression analysis. And that brings us to the end of our deep dive into the assumptions of regression. Remember, solid assumptions lead to solid conclusions. So it's always crucial to check this before running your regression analysis. If you enjoyed this journey through the intricacies of these key statistical assumptions, don't forget to hit the like button. Your feedback helps us create better content that meets your learning needs. Subscribe and hit the bell icon to ensure you don't miss our next adventure into the data wilderness. And as always, leave your questions, thoughts, or topic you would like us to cover in the comments below. This is Raffaele, reminding you that the journey of learning statistics is not about the destination, but about what you understand along the way. Stay curious, stay engaged, and keep wanting to become tomorrow's leader.